So before we can talk about gravity, we need to talk about a little bit of history as to how we discovered how things move in the heavens based on primitive observations. Okay? It's amazing how much people were able to learn, measure, discover, okay, and even kind of hypothesize about without understanding what gravity was. Okay? We had tons and tons of theories about why and how celestial bodies move through the sky without having any understanding of the force of gravity. Okay? The fact that we were able to do that is actually pretty amazing because gravity is what causes all of that to happen. Okay? Unfortunately, many of our ideas about how things move were wrong. Okay? And the reason for that is we can only observe them from Earth. So our reference to their motion is a little bit skewed. Okay? So we'll start out with the main idea, or the first idea about how things moved in the heavens was that everything orbited what? Right, everything orbited the Earth. Okay, it was what we called the terracentric universe. Right, everything orbited the Earth. Which, if you are not understanding gravity and you just watch things move in the sky, actually makes perfect sense. Okay, because you watch the sun rise and set every day. It makes it look like it's going around us, and not that the Earth is spinning on its axis. Okay, we watch the moon rise and set. Makes it look like it's going around us. Okay, it was a perfectly logical assumption for people to make. Unfortunately, it was so logical that it was very difficult to convince people otherwise. I mean, for God's sake, there's still people out there who think the world is flat. They're crazy. Crazy. With a capital K. Okay? That crazy. But, okay, there's still, it's hard to break people's ideas sometimes. Okay? So, what we're going to look at here is kind of how we discovered that things don't move that way, and some of the people involved. So, Johannes Kepler, probably one of the most important scientists in regards to breaking the idea of the terracentric universe and proving that things actually do orbit the sun. Okay, again, all without understanding what gravity was. Okay, so he was a German mathematician, and he had a strong interest in astronomy, and he started working for this incredibly famous, well-respected astronomer named Tycho Brahe. Now, so begins one of the most dramatic relationships in the history of science. Like, these two guys went to their grave hating each other's guts. Okay? Like, this was a pure and utter hatred, and I'll explain why. Okay? Tycho Brahe spent his entire life observing the movement of objects in the sky. Okay? Especially the movement of the planets. Right? He knew which kind of stars in the sky were, Mars, and which one was Venus, and which one was, Jupiter and Saturn, and all of that. And he made these incredibly accurate, detailed observations over the course of his entire life. It was his life's work. But Tycho Brahe believed in a terracentric universe, that everything orbited the Earth. The problem was, he had some observations, carefully measured, repeated observations that didn't agree with his idea that everything orbited the Earth. The main one being this. When he observed Mars moving in the sky, Mars would move like Venus does and like Mercury does. Okay? It would move around. But then at one point in its orbit, instead of continuing to move along this path, Mars would move backwards in the sky and then start moving forwards in a proper orbit again. And it would do that on a very regular basis. Now, obviously, something orbiting the Earth doesn't stop, back up for a couple of weeks, and then turn around and go the right way again. Okay? The planet just doesn't do that. Right? But he couldn't figure out why he kept seeing this thing happen over and over and over again. And he couldn't come up with a reason. So, he hired Johannes Kepler. Because Johannes Kepler was good at math. And he figured, there's got to be a reason for this. I'm just not good enough at math to figure out what it is. So, here, Kepler, take all of my life's work and prove me right. Do your math magic. So, Kepler takes a few months to look over this guy's stuff, comes up with some math, and goes, all right, I'm going to get fired. And I'm going to get fired because this guy has incredibly accurate, detailed observations that prove he's wrong. Okay? Can you imagine your whole life's work is only going to do one thing, and that is prove you are wrong about what you have believed your whole life. And you just hired a guy to tell you that. Okay? So Kepler didn't want to get fired, so he kind of delays for a while. Oh yeah, I'm working it out. It's there's a couple of little things here. I'm just solving for some variables. How am I going to tell this guy his whole life's work is wrong? But then eventually he says, "Look, I'm good at math. That's why you hired me." The math says you're wrong. The math says that the sun is the center of our solar system, and the sun orbits the center of the galaxy. The Earth is not the center of the universe. To which Tycho Brahe promptly replied, "You're fired!" Because that was what he wanted to hear. Okay? You must not be that good at math. My detailed observations can't prove me right. Okay? This is why Mars does this. Because Earth orbits inside of it. Which means every once in a while, Earth passes Mars in its orbit. Now, if you're in a car on the highway and you pass somebody, okay, when you're coming up to them, it still looks like they're moving forwards. But as you pass them, it looks like they're moving backwards until you're a little ways ahead of them, and then you can tell they're moving forwards again. It's exactly the same when one planet passes the other planet in its orbit. So as Earth goes by Mars, because it's moving faster, because it's got a smaller orbit, it looks like Mars moves backwards in the night sky. And then Earth gets far enough ahead of it that it looks like Mars is going forwards again. Okay? Mars doesn't actually do that. It just gets passed by us on a regular basis. Okay? Everybody kind of follow me there? That's what Kepler figured out. And after Brahe fired him, he still had all of Brahe's notes. So he went on to publish a humiliation of Tycho Brahe and used his life's work to prove his own ideas about how things actually moved in the sky. So you can imagine Tycho Brahe would have been just a little joke about that. Okay? This guy took all of his life's work and humiliated him with it. Okay? Made him look like a fool in the scientific community, okay? Because he actually had, Kepler that is, had the math right and was able to prove from Tycho Brahe's own notes how everything mechanically moved. Okay? So, Kepler's laws say this. First off, orbits are not perfect circles. Okay? Basically, nothing orbits anything else in a perfect circle. Okay? All orbits are slightly elliptical. Okay? That is to say, they're not a basketball, they're not a football either. Okay? They're somewhere in between. Okay? Most of them look pretty much like a circle, but they're not a perfect circle. Okay? So Kepler used his data to determine that a planet must revolve around the sun. Kepler also hypothesized that Mars had an elliptical orbit, not a circular one. Okay, and so as a result, this is what he saw. Now this is greatly exaggerated. Okay, the Earth's orbit does not get this close to the sun and then this far away from the sun. This is greatly exaggerated. Okay, if this was the case, Earth would periodically fry and freeze and fry and freeze. Okay, but we actually do get closer to the sun at different points in our orbit. Okay? Actually, no, it doesn't cause the seasons. What causes the seasons? The Earth's tilt causes the seasons. We're actually closest to the sun right now. Okay? We're closest to the sun during the winter. Now, there is a fluctuation of this. Okay? The Earth goes through different periods where, because of its rotation and because of the wobble, essentially, of the Earth back and forth, okay, that they're over long time spans that will actually change. There will be times in the future where we're at perigee closest to the sun during the summer, and times when we're close to the sun during the winter. We just happen to be during one of those times right now. It's called precession. Okay? I'll actually show you a video on it here in a few minutes. Okay? But the Earth's orbit is elliptical, okay? But that's not what causes the seasons. What causes the seasons is, so here's the sun, okay? Here's the Earth's orbit, okay? And the Earth is tilted. Okay? So that's the Earth's axis. Alright, so as the Earth goes around the sun, okay, in its orbit, okay, right now, at this point in the orbit, Earth would be in what season? I'm sorry, we would be in what season? Winter. Okay? We would be in winter because we're tilted away from the sun. Okay? The North Pole is tilted away from the sun, which means we don't get into the sun as much. That's why the days are shorter in the winter. Okay? Not only do we not get in the sun as much and days are shorter, but the intensity of the sunlight is less because it's not directly overhead. Okay? I don't know if you've noticed, but the sun doesn't get very high in the sky in December. Okay? If you're looking at the horizon, okay, the sun does this pathetic little arc, okay, across the sky during December. And if you live in the far north, it's even worse. If you're above the Arctic Circle, you don't see the sun. Okay? You're tilted so far away that as the Earth rotates around and around on its axis, because you're way up here, you never get into the sun. You're always in the dark. Okay? And so in the Arctic Circle, they can have, almost 8 weeks of total darkness. Okay? And then the days get longer and so on. And then, of course, in the summertime, we look like this. And the North Pole is tilted towards the sun. As the Earth rotates like this, the sun never sets. It goes in a circle. It's really weird. Okay? If you've ever been above the Arctic Circle in the summertime, the sun literally does this. It makes a loop in the sky above you. Okay? Because it never sets. You're always pointed at it, but it makes this circle in the sky. Okay? And it's always light. It's crazy.
Like if you're closest to the sun, why is it now?
Because the distance from the sun actually doesn't change that much. Not enough to make a huge difference, a small difference. But what mainly causes our change in temperature is the directness of the sunlight, how overhead it is, and how much of it, how many hours a day that we get. Okay? Certainly being closer to the sun doesn't even get more solar radiation, but because we're tilted away from the sun, it doesn't make that big a difference for us. Make a bigger difference for an equatorial. Okay? All right, and then obviously these, okay, so these two spots here are the equinoxes. Okay, that's when we get 12 hours of sun and 12 hours at night. Okay, and this is the winter solstice coming up on us in less than 3 weeks. Okay, shortest day of the year, summer solstice. That's an M. Okay, longest day of the year. That's my favorite day. I love the summer solstice. It's light for 18 and a half hours. Okay, not so much on the other side of that, but it's light for 4 hours. All right, that's sort of making sense. Okay, so the Earth's orbit is not a perfect circle, it's actually an ellipse. So there are times when we are closer and times when we are further away, okay? And that's something that Kepler discovered, because he found that the Earth moved at different speeds through its orbit by using Bray's data. He could see how quickly other stars moved in the sky, and based on that, he could tell how fast the Earth was moving. Okay? And he knew that the Earth changed speed as it moved. The only way the Earth could change speed as it moved around the sun was if the force causing it to move in a circle changed, right? Because Fc is mv squared over r. And the only way for us to go faster is if either this force changes or this number changes. Okay? Since we didn't really know about gravity yet, that really wasn't the part of the equation he was worried about. It was this. The Earth has to get closer to the sun in order for it to move faster. Okay? All right. So Kepler's first law is what we call the law of elliptical orbits. Okay? The planet moves in a path around the sun that is an ellipse. Okay? So not a perfect circle. Okay, so when we look at our formula sheet, if you pull out your formula sheet and you look at the back, okay, it's got the average Earth-Sun distance written on it. Okay, the average Earth-Sun distance is 1.5 times 10 to the 11 meters. But again, that's listed on your formula sheet as an average. The Earth's orbit is elliptical, that number changes over time, okay, and throughout the Earth's orbit. Sometimes it's bigger than that, sometimes it's smaller than that, but that's what it is on average. Okay, it's the same for the moon. The moon's orbit is also not perfectly elliptical, perfectly circular. It is somewhat elliptical, okay, and so as a result, that 3.85 times 10 to the 8 number is an average.
How much does it?
Well, I'm going to show you here in a minute. Okay?
How do they calculate the distance from the sun?
A lot of different calculations, a lot of different calculations. Probably multiple different ways and then averaging it. Okay, so if we're looking at, that law of elliptical orbits here, the eccentricity numbers that are listed here, okay, this is essentially how far off of a perfect circle each planet's orbit actually is. All right, so Mercury actually has a fairly elliptical orbit. It's over 20% off of being a perfect circle. So quite elliptical. Okay? Venus, on the other hand, is almost a perfect circle. Okay? Its orbit is almost a perfect circle. It's less than 1% away from being a perfect circle. Okay? Earth, okay, its orbit is 1.7, somewhere around there, okay, percent off of being a perfect circle. So not a huge amount, right? Like that distance between Earth and the Sun changes a bit, and seems like a big number when we look at it. But when we talk about how far the Earth is away from the Sun, it really isn't all that much, about 1.7%. Okay, Mars is almost 10%. Mars's orbit is actually quite elliptical, and part of the reason for that is Mars is closer to Jupiter than we are, and Jupiter's big. Okay, Jupiter pulls on Mars actually quite a bit and causes its orbit to become more elliptical. Okay, Ceres is an asteroid in the asteroid belt. Okay, basically it's a dwarf planet within the asteroid belt. Okay, and it has a fairly elliptical orbit. Okay, Jupiter, okay, also an elliptical orbit. It's got the influence of the Sun, but also the influence of Saturn and the other ice giants behind it. Okay, Saturn, okay, about 5%. Uranus, that's by the way how you pronounce it. It is not a part of your body. Okay, Uranus. Okay. Neptune, almost a perfect circle, less than 1% off of being a perfect circle. But look at Pluto. Okay, it's 25% off of a perfect circle. Okay, and not only that, it doesn't actually orbit in the same plane as all the other planets, which is why it's no longer considered a true planet. Okay, it is a dwarf planet because it's not the largest thing in its orbital path. Okay, and its orbit is highly elliptical and outside of the ecliptic. What we mean by that is this. So here's the Sun. This is the plane in which the 8 planets orbit. Okay, so they can eclipse each other because they all lie in the plane of the ecliptic. That's not enough circles. Okay, Pluto does this. Okay, its orbit is highly elliptical, and at times it is closer to the Sun than Neptune is. So it actually crosses Neptune's orbit and comes inside of it periodically, right? Which is why it's no longer considered a true planet. It does not dominate its orbit. Neptune is in its orbit, okay? And its orbit is outside of the plane of the other. So you can't eclipse Pluto, okay? Pluto would never have a solar eclipse, okay? Because none of these other planets can move between it and the Sun, okay? And block the Sun's light.
Pluto, like, smashing their
It theoretically could, but it would be highly unlikely. The volume of space we're talking about out there is too big. Okay? All right. Now, the other thing is, once Kepler came up with this idea of these law of elliptical orbits, he was basically required to show some mathematical proof. So his second law is actually the mathematical proof of his law of elliptical orbits. So his second law is what we call the law of equal areas. Okay? So if a planet has an elliptical orbit like this, okay, it moves at different speeds depending on where it is. It would move fastest during this part of its orbit here. So use a different color. Okay, and it would move fastest during this part because its radius is smaller. It's closest to the Sun. Out here, it moves the slowest because it's furthest from the Sun. But the area it sweeps out in all of these sections is equal, or they are equal. Right? Okay. This one obviously goes further around the orbit, but the radius isn't as big. This one doesn't go as far around the orbit, but has a much larger radius. So the areas are actually equal, and he proved it mathematically. Okay? Which then was the mathematical proof of the fact that yes, planets can move in elliptical orbits. Okay? All right, now, if we're looking here at the changes in speed, okay, for the Earth, Okay? When the Earth is at perigee, that's closest to the sun, it moves at 109,289 kilometers per hour. So it's trucking. Okay? It moves pretty fast. Okay? When it's at apogee, which is the furthest from the sun, it only moves at 105,635. I say only, but I mean it's a difference of 4,000 kilometers per hour. Okay? Now, I know right now you're thinking 4,000 kilometers an hour is a lot for there. Yeah, it is to us Earth dwellers, but you don't really notice it when you're talking about how far the Earth has to go in 1 year. Okay? Incidentally, 1 year is how long? Nope. 365.240 something, yes. Okay? That's why we have a leap year every 4 years. Okay? We need to have a leap year every 4 years to make up for that quarter of a day. Okay? In every orbit that we're out. Okay? So every 4 years we make up that quarter of a day. Alright, now I'm going to show you kind of how this works, this law of elliptical orbits, plus this whole wobbling back and forth thing that the Earth does. Okay? And because this guy actually did a pretty good job of it. Alright, so we got these elliptical orbits, we got these equal areas, okay, and then came Kepler's kind of biggest piece of the puzzle, okay, and that was he discovered that if you took the period of any planet in the solar system and squared it and divided that by the radius of that planet's orbit cubed, you always got the same number. Every planet in the solar system gets the same number. Okay, it's called Kepler's Constant. Okay, so if I take Jupiter's orbital period, square it, and divide it by the distance between Jupiter and the Sun cubed, I'll get the same number as if I do that exact same operation with Earth's numbers, Mercury's numbers, Mars' numbers. I'll always get the same Kepler constant. Okay? The only way that could possibly be true is if they all orbit the same central point. Okay? That's the only way that that could happen. Right? So that was kind of his last piece of proof against Tycho Brahe. Okay? And of course used Tycho Brahe's data, because all of Tycho Brahe's data was on how long it took all the planets to complete an orbit and how far away they were. Okay? So again, using all of Tycho Brahe's life's work, okay, to prove him wrong. All right, so that's what I just showed you here. Okay, the period of any one object in the solar system divided by the radius of its orbit cubed will give you a Kepler constant, which means you could set them equal to each other. Okay, and that's effectively how we can determine the location of other objects that we may not be able to observe visually. Okay, we may be able to use that to predict where they are, and that was to some extent how we discovered the planets beyond Saturn. Okay? Those are not planets that are visible to the human eye in the night sky. Okay? So Uranus and Neptune, Pluto, okay? Those were all discovered by calculating where they would be and then pointing a telescope to that spot. Okay? They were not actually visible in the sky before. All right. Is everyone okay with this formula? We're going to do a couple of problems related to this formula. It's pretty easy to use. Okay? Now, the nice thing about Kepler's formula here is that it uses numbers that can be, let's say, shortened. Okay? When we start using forces to determine where things are, we have to use all these big numbers because they always have to be in meters. Period always has to be in seconds, okay, and things like that. But with Kepler, okay, the period can be in any units you want. It could be in seconds, it could be in years, which means if I do this in years, the period is a nice small number. Right? If I'm looking at the radius of the orbit, that can also be in any units I want. Okay? If it's in meters, it's going to be a really big number. But if it's in kilometers, it's going to be much smaller. Or, even better than that, I might be able to use something called an astronomical unit. Okay? 1 AU is the distance from the center of the Earth to the center of the Sun. Okay, so we often use astronomical units instead of meters because, again, rather than use 1.5 times 10 to the 11, I would much rather use 1 because that's a much smaller number and much easier to do math with, okay, than 1.50 times 10 to the 11.
Would we ever have to convert?
If you did, it'd be really easy. Either multiply by 1.5 times 10 to the 11 or divide by 1.5 times 10 to the 11, right? So if I have 2 astronomical units, it's 3.0 times 10 to the 11. But yeah, you might have to, but it's super easy. It's not like kilometers per hour and meters per second. It's way easier than that. Okay. So I would like you guys to write down the stuff that's in yellow there along with the titles. These are Kepler's 3 laws. Okay? This would be a really easy multiple choice type question, like which of the following would Kepler not have agreed with? Or which one of the following is not one of Kepler's ideas? Okay? And it would be whichever one isn't one of these 3. So I'll give you a few minutes to write those ones down. All right, so Kepler's 3 laws are the law of elliptical orbits, okay, which basically tells you that all planets have elliptical orbits with the sun at one focus. Okay, the second one's the law of equal areas, okay, and that was kind of the proof of planets move in elliptical orbits because their radius changes, and that causes changes in speed. Okay, so that was his law of equal areas. And then the last one was the law of periods, saying that the period squared over the radius of the orbit cubed will always give us the same constant for all objects orbiting the same central point. Okay, so all objects orbiting the sun have the same Kepler constant. All of Jupiter's moons would have the same Kepler constant because they all orbit Jupiter. Okay, any objects that share an orbital center will have the same Kepler constant. Okay. All right, so moving on to kind of the math of Kepler's law of periods here. It's not difficult, but we're just going to look at a couple of examples here. Okay, so we use astronomical units and we use years usually when we're using Kepler's law of periods, just because, again, they give us smaller numbers to do with.
How did you know the radius in the first place?
Again, they would have been determined by how long it would have taken things to make one complete orbit. They wouldn't have been as accurate as they are now, okay, without being able to measure things with satellites and things like that. But they would have used orbital periods and comparisons to other objects to come up with these numbers. They would have used a couple of different ways and then probably averaged them. Okay. All right. So if we're looking at, let's say, this example here, so if I can have everybody just write this example down, we're going to use this to show you how Kepler's law of periods works. Okay. So in this example, we have Mars. And Mars has a orbital radius of 1.52 astronomical units. That means it's a little bit more than 1.5 times further from the sun than Earth is. Okay? We want to figure out what its orbital period is. Now, because they didn't specify what units they want that orbital period in, we should probably pick years because it'll be a nice small number. Okay? Now, Kepler's law of periods says that the period of any one object squared over the radius of its orbit cubed is going to give me the same number as a second object sharing that same orbital point. All right, now, in order to use Kepler's law of periods, I need to know information. I need to know T and R for at least one of the two objects. Okay? So do I know the orbital period and the orbital radius of another object orbiting the sun besides Mars? Yes, I do. What planet do I know them for? Earth. Exactly. All right, so what I'm going to do is instead of using ones here, okay, I'm going to make planet 1 Earth. And I'm going to make planet 2 Mars. Because they tell me the orbital radius of Mars in the question. Everybody all right with that? Okay. So I'm looking for the period of Mars. I'm looking for T. What do I need to do with R cubed? Multiply it over to this side. Okay? So what I'm going to have is T of Earth squared times the radius of Mars's orbit cubed divided by the radius of Earth's orbit cubed equals the period of Mars squared. Now, do I want the period of Mars to be squared or do I want it to be normal? So what do I have to do? Square root. Okay, so if I square root that, that goes away, and then I just square root this side. So now I got to plug in my numbers. The period of Earth's orbit is 1. Okay, so 1 squared is 1. Awesome. Okay. Multiply that by the radius of Mars' orbit, which they told me was 1.52 astronomical units cubed. Okay. Divided by the radius of Earth's orbit in astronomical units. 1. What's 1 cubed? 1. See how easy this gets? Okay. You get to use these these little numbers. Okay. And so in the end, all I have to do is take the square root of 1.52 cubed. All right, so to cube things on your calculator, you're going to have to hit the math button. So we'll go with second function, and then we'll go 1.52, and then you hit math, and you can make a cube by hitting 3, or you can get a cube root by hitting 4. All right, so that says that it takes Mars 1.87 Earth years to complete one orbit. Okay, so not quite twice as long, but close. Okay, almost twice as long to orbit the Earth, to orbit the Sun one time as. Okay, everybody all right with that? So, nice thing about Kepler's law of periods is it's great if I have the right information and I have two bodies orbiting the same central point. Basically, you very rarely ever get that information. Okay? Most of the time when we're talking about period of an orbit, we're going to be setting centripetal force equal to the force of gravity and doing it that way, which I haven't gone over yet. That's what I'm going to go over tomorrow. Okay? But we're looking at Kepler today. So. All right, I want you guys to see if you can answer these questions using Kepler's law of periods, which is what we just did there. Okay, give you a few. So, for question number 1 here, we're going to try and figure out what the orbital period of Jupiter is. So it's exactly the same thing we did on the previous question with Mars, except now we're using Jupiter's information. So we're going to say that the period of Earth squared over the radius of Earth's orbit cubed equals the period of Jupiter squared over the radius of Jupiter's orbit cubed. Okay, so we're trying to find the period of Jupiter, so we're going to multiply both sides by the radius of Jupiter's orbit cubed, okay, and then take the square root of that to get us the period. Okay, so that's going to be then 5.203. So Jupiter is more than 5 times further away from the Sun than Earth is. Okay, and that's going to be cubed multiplied by 1 squared divided by 1 cubed. Okay, everybody all right with that? Because we're using astronomical units here and years for our units per period. Okay, so basically we just want to take the square root of 5.203 cubed. All right, so a year on Jupiter is 11.9 Earth years. Okay, actually we have 4 significant figures here, so 11.87 Earth years. Now we've done number 2. Okay, are we ready to go over number 2 as well? Yes? So for number 2, okay, it says that it takes Pluto 90,553 Earth days. So what does the period of Earth need to be in this question? Days. Okay, I've got to put it in days, which is 365.25. Okay, if you don't put the 0.25 in, it's going to make a difference. Okay, which is why I made kind of a big deal out of that earlier. All right, we're trying to determine the orbital radius of Pluto. So we're going to have period of Earth squared over radius of Earth's orbit cubed equals the period of Pluto squared over the radius of Pluto's orbit cubed, and that's what I'm looking for. So I'm actually going to bring that up over here, so it's on the top when I solve for it, okay, and then I'm going to move everything else. Okay, and then I'm going to have to take the cube root of that. Okay, so I'm going to have that the radius of Pluto's orbit equals the cube root of 90,553 Earth days squared, okay, times 1 cubed, okay, divided by the period of Earth, which is going to be 365.25 squared. So as long as my units all match, I can use whatever units I want. Okay, I just have to make them match. So we've got 90,553 squared, okay, divided by 365.25 squared. Okay, so Pluto is, sorry, that's not the right answer because that's not the cube root. It's the square root, and I need the cube root. 4. That's better. Okay, so Pluto is almost 40 times further away from the Sun than Earth is. Long, long way. Somebody fully done number 3? Okay, I'll give you a couple more minutes on number 3. Okay, let's have a look at number 3. Oh, I was recording that whole time. It's going to be a big dead spot. Okay, so for number 3, we got a piece of rocky debris in space with a mean orbital distance of 45.0 astronomical units. We're looking for the orbital period. So again, we're going to use the period of Earth as one of them, okay, and we're going to use the rocky debris as the other. Okay. So we're just going to bring the orbital radius of the rocky debris over to here, okay, and then square root everything. Okay, so we'll have that the period of that rocky debris is the square root of 45 cubed plus 1 squared, or sorry, times 1 squared divided by 1 cubed. Okay, and so basically we're just looking at 302 Earth years, so that would be definitely something out in the Kuiper belt, okay, beyond the orbit of Pluto, okay, something like that. All right, 2 more. is Tuesday. You haven't had a quiz for a while. You have one tomorrow. Okay? It'll be probably vertical circular motion, so be ready for that. Okay? Remembering, guys, okay, a couple of changes here. Circular motion assignments are due tomorrow. Okay, make sure you got those done. Okay? Unit 2, Unit 3 exam moved to December 12th. Rest head assignment December 19th.